All right, so thank you everybody for joining us today. Everybody should know if we have Dino Esposito with us today, talking about building a recommender system in ML.NET. So Dino, thank you so much for joining us, and I'll turn it over to you.
Okay, hi everybody. It's Dino Esposito here. With me, there is also Francesco Esposito, who is the brains behind most of the mathematics that we apply every day. We work in a business domain that has to do with data points in the real sense of the word. So because we are in the sport tech industry, and what is called data point in machine learning is actually data regarding a point physically played on some court, whether it's a tennis court or a football court. So we are still talking in our everyday business about points that are really played points somewhere. Okay, but the talk of today is about one of the canonical topics on machine learning, how to build and how to understand the behavior of a recommender system, just a Netflix, Amazon Prime Video style kind of tool that suggests what else you can do with the platform, which other movies you may enjoy given your past experience. So this is essentially the point of this presentation today. Let's start with a few core definitions. So what is a recommender system? It is a system that collects data from many users with the purpose to guess the preferences of each user. A recommender, that's an important point to keep in mind, will not receive direct input from the user. A recommender is not exposed directly to the user. Of course, a recommender will work on top of what the user may have done in historical interaction with the system, but there is no direct contact between a recommender and the user. And at the same time, the recommendations that the system provides out of this kind of module are in a way sparse, in the sense that multiple recommendations tend to refer to items that are distant from each other, just to try to cover altogether a good range of chances for the user to do the next step within the host application system. Opposed to a recommender system, we find a ranking system. They are not the same thing, though they are in a way related. A ranking system is the classic example of a ranking system is the Google PageRank algorithm. So a system that is expected to measure the relevance of documents within typically an information retrieval system, but an information retrieval system of any kind. So based on documents, but also based on whatever piece of information we can wrap up in a sort of a digital container. A ranker, as opposed to a recommender system, receives direct feedback from the user. Think again to a classic canonical Google style query. Conversely, results you receive from a ranking system are expected to refer to very similar, very close to each other items. If I want to search on documents on a geography, or the geography of a certain area of the world, I expect to find documents that refer exactly to that specific area. Now, a few more on core definitions. Both recommenders and ranking systems, in summary, try to help the users of a system to get as close as possible to what they are looking for, and those systems try to replace the user, try to suggest, to be in the mind of the user, to try to guess what they would enjoy doing or viewing or interacting with in the further interaction with the system. However, both types of systems, but especially recommenders, are subject to an issue that is the possible lack of interpretation of the results. So the results you get may be sometimes hard to make sense. Still, they are considered recommendations. If you don't get enough the point, think of when Netflix or Amazon Prime Video recommended this is a movie you might like, and you have no idea you may like that movie. So this is an example in which the system has produced some piece of recommendation, but it is not specifically in the preferences of the user. So recommending is a very delicate art. Users typically have no way to check the quality of the suggestions, and the same can be said for the system. So a suggestion comes out of a black box, and it's very problematic, just hard to measure the real effectiveness, quality, relevance of that suggestion. Users can only follow the suggestion in a sort of trust but verify approach. Now, is explainability, the whole topic of explainability, something that can be of help here? Maybe, but at the moment, explainability, the idea around the whole topic of artificial intelligence and machine learning, the branch of it that attempts to find measures, mathematical measures of how good is the working of the model. I'm not talking about the error, but in the ability of understanding the importance of the features that are manipulated, and then the quality of the result, and the reasoning that the machine learning algorithm has made. So this whole point of explainability is very young at the moment for the industry. So for the masses, at least for wide use in the industry, is fairly young, but is growing up. And we have a framework called SHAP, which is very friendly to use in the Python environment. On ML.NET, on the Microsoft.NET stack, we have something called permutation feature importance, which is very promising. But in our opinion, those tools related to explainability are relatively young for the time being. And in summary, why recommending is considered a delicate art is because it's a problem that is very simple to make sense of, yet it is problematic to implement. So in the industry, the whole spectrum of ranking solutions move from very naive solutions to fairly sophisticated solutions, because you want to give solution to the problem of helping users making the next choice within a system. Typically, you have a very relatively easy way to do it. If that very easy way doesn't work, the only other option left is a very sophisticated way of doing those things, and almost nothing is left in the middle. Now, there are a couple of three slides probably in which we try to insert in this discussion, general purpose discussion so far on recommenders. We want to inject some direct knowledge of the matter that we have matured in our sport tech industry. So one of the projects we are elaborating on just these days is called MatchMatcher, and essentially it's based on the basic idea that an existing system that users use to place dynamic queries to obtain results of sport matches. So the user enters a query and they select a range of matches. Now we want ranges of matches that they have reasons to be interested in. So in this media segment of the sport tech industry, the primary purpose of this system is bringing up interesting things to say, for articles and posts to be created, for commenters to mention during live matches. So the purpose of this MatchMatcher system is identifying matches that have some points in common with the matches that are the subject of the latest research, the latest query. How we are thinking we are working actually on making this a piece of real software. In machine learning, if you open up any book, if you open up any website that promises to talk about it, you find algorithms everywhere, and those algorithms more or less match to a general purpose classification of problems. So these algorithms are all for a relatively well-defined, restricted tasks. But real-world problems hardly match perfectly any of the tasks and algorithms for which a known solutions, a canonical solution is known. So most of the time in the real world, it's the real effort is about breaking up the problem into connecting parts and then solving those parts one at a time, and connecting the solutions together to form a pipeline that is more than a training pipeline, is a real learning pipeline. So back to our MatchMatcher idea, what we're trying to do is place results of the query. So for example, football matches has points within an n-dimensional space, where n is essentially the number of columns in the data set we end up to consider. One way we are experimenting with is using autoencoders, and this is the hardest part, to try to essentially reduce the essence of a match, for example, a football match, to a sequence of coded values. But anyway, you can think of those matches as points in an n-dimensional space. And then we plan to use basic mathematical tools like clustering algorithms like KNN, or even more mathematical stuff like cosine similarity, to find items in the same n-dimensional space that are at a short distance from the subject of the latest user query. And then algorithmically we pick up the top k items that seem to be similar to the latest query, and once we have found an encoded content for a match in this as a point from this n-dimensional space, we have some algorithmic code that is outside the realm of machine learning that match those encoded values back to a real match that has been played that we have in the database. And then finally, the hardest task is presenting those selected matches with a clear justification to the user, with a sentence like, you might want to dig these matches further because they are related to the latest research based on because of this, and that. And this is the point where explainability and SHAP that we are working with, for example, comes into play. So in the end, our MatchMatcher is not exactly a canonical recommender system like those you may experiment with, you may experience when you use Amazon Prime Video or Netflix, but yet it is a recommender system completely custom, in which a bit of clustering is used to group queries together, and then a cluster, the largest cluster, or a cluster that is reckoned to be relevant by some conditions, is selected, and the points in this cluster are matched back to actual football matches presented as a list ranked by relevance to the end user of the system. Okay, but this said, so and this was just to give you a concrete real-world perspective on ways in which we can use, creative ways in which we can use the principles of recommenders in machine learning and in areas of the real-world business not so commonly touched by the idea of recommending. Anyway, now let's go ahead and let's start talking ML.NET. Now, our take on ML.NET is a little bit probably out of emphasis in the sense that we consider ML.NET full of ready-made toys to practice machine learning using C#. Now, the word toys doesn't have to be intended as a way to disregard ML.NET as a platform. We love it, but at the same time, ML.NET was built by design since the very beginning as a collection of practical tools, so they call it tasks, for developers, .NET developers, combine together complex solutions using C# in their favorite C#.NET environment. So it's a way to reduce the number of situations and scenarios in which you have to resort to Python, typically Python, to solve a problem. ML.NET just offers within the familiar .NET Framework core more powerful classes, more powerful tools to just write sophisticated, intelligent algorithms. Now, again, when the problem to approach with machine learning is straight, clean, understandable, and when it really maps closely to one of the canonical algorithms, one of the canonical predefined tasks you find in ML.NET, then everything is great, everything is easy, everything is fast and effective. But this works great for demos, and in the real world when you don't have particularly sophisticated things requested by customers. We would like to say that ML.NET is a kind of entity framework for machine learning. So it's a framework that does great things in a fraction of the time you need to employ if you would do everything by hand or with lower level tools, but it's not exactly the tool that is good for it. It is a great fit for every possible scenario. It's very ML.NET on the other hand is very developer friendly, and in the time that this presentation takes, we will see also an ASP.NET Core application that consumes a model trained using the classes of ML.NET. So let's see what it takes to tackle the topic of recommendation with ML.NET. So the idea is given a list of movies, so a data set made of a list of movies, we want to try to predict which movie would be of interest for a given user. Under the hood, the recommender estimates, tries to discover the rating the user would assign to a given movie, and then labels it as you will like it if the rating exceeds a fixed threshold. Otherwise, it will label it as you might want to give it a try, you may not like, or we don't recommend this. Now, the way in which you label the score calculated by the recommender for a pair user movie, that mostly depends on what you want to do as a developer, as the author of the application, how much you want to be friendly to the user, exactly what is the things that you want to show to users. So you will like it, you will not like it. It's everything built as a syntactic sugar to keep the end user happy. From the digital component of the recommender, all that you get is a float number. And then that float number refers to a kind of threshold, and it's up to you to decide how much sugar you want to add, depending on the distance between the score float number and any given fixed threshold. Now, you see here a screenshot from an Excel file, and This is the typical basic but representative data set for a recommender module. There are 3 columns: user ID, movie ID, and then the rating. And in an obviously fully anonymous way, it identifies a user, a live user of the system, a reference to a movie, and then how that user has rated that movie. This data that you see represented in a CSV Excel style form has been ETL'd from some production system. So it's not data you find probably exactly in that way within a SQL Server table or within any sort of data warehouse, data lake you may have, but it's something you likely create extrapolating data from some one or even more external systems. But anyway, that is the list of columns that a recommender needs to work on. Now, when it comes to recommenders, there is one basic fundamental algorithm, and it's called the matrix factorization algorithm. There is a very funny story about this algorithm. This algorithm was devised, if I remember correctly, already in the 80s, so several years ago, a few decades ago. And it was one of the tools for those people that decades ago were practicing artificial intelligence and machine learning. As you may know, artificial intelligence and machine learning are not at all new topics, but I can tell you that when I graduated, and I graduated back in 1990, already at that time, it was fairly common for my peers to defend a thesis for graduating on some topics tightly related to machine learning and neural networks and artificial intelligence. And that was something like 30 years ago. So after that point, late 80s, early 90s, that we faced in this area of the technology what was called one of the many winters of AI in which nothing happened, mostly because of money, of missing funds, and we observed a slow return towards interest in artificial intelligence with the new millennium, when, for example, Microsoft started adding silently under the hood smart, intelligent algorithms in Office applications. And, for example, most of the code and the ideas, more than the code we find today in ML.NET, date back to the things that Microsoft experimented silently over the years, mostly with Office applications, and not just that. But anyway, most of that old work was done for PowerPoint and for Excel and Words. But anyway, so the matrix factorization algorithm is nothing new and has been available to researchers for several years. But all of a sudden, around 2006, it became extremely popular and received a boost in performance and power. Why? Because in 2006, Netflix, the Netflix of the time, which was a much smaller company than the giant it is today, Netflix decided to challenge the data science community with a prize, I think was something like $1 million prize, for the team of scientists that would have produced an algorithm, a recommender algorithm, more powerful than the algorithm that Netflix had in production at the time. And again, the purpose of Netflix, guess what, was predicting much more closely how much someone would have enjoyed watching a given movie. In the end of the story, the prize was awarded to a team from several institutes of research that went from the US and even from Europe, so from several parts of the world. I think it was 3 different teams. The winning team was globally known as the baleful pragmatic chaos team, and they won with an algorithm that was a variation of the classic matrix factorization algorithm. A variation in the sense that it was using an ensemble approach to train multiple matrix factorization algorithms simultaneously and then combining the results together. The ensemble approach, in general terms, is when you use in parallel multiple differently configured instances of the same algorithm, and then you obtain multiple models, and then you build out a single model out of the content found in the simultaneously produced submodels. And the combination of n models into a single model was done using a very sophisticated non-linear function. Don't ask me details on what this algorithm, it was called a non-linear blending function, which was blending together the numbers produced by multiple matrix factorization differently configured to obtain the final result. So that was the story that brought back again to popularity the matrix factorization, and this variation created to win the $1 million prize awarded by Netflix in 2006 is today the most common implementation of the same matrix factorization algorithm, which, because of this Netflix contribution, grew to the next level of effectiveness. Now, the matrix factorization algorithm is it's very simple. Again, it can be explained effectively in with very few words. Basically, it takes 2 steps. Step number 1, you get a user and the movie pair. And then the algorithm, that's the input. And then the algorithm looks for other users in the provided data set that rated the same movies that the given user rated. So the point, the output of the first step of the algorithm is coming up with a list of users that have or may have the same preferences. If any of the users in this subset, so of users with similar preferences, if any of this rated that specific movie, then the expectation for the input user is calculated as the average of the available ratings that similar users have specified. Apparently, it's understandable, it's reasonable, makes sense, but there are some issues, 2 particular issues. What if there are no ratings whatsoever for that particular movie? So in other words, I can still find, the algorithm can still find effectively a number of users with the same interests from the data set. But when it comes to this, to determining how each user in this group would rate a particular movie, it is mandatory that some existing ratings are in the system from users in that group. What if this is not the case? What if there are no ratings whatsoever? And this could be the case because there are too many new users in the system, or inactive users, or the movie is new or really, really unpopular. So there is no guarantee whatsoever that we have that the recommender system will find every single time enough data to make a sensible calculation. When this happens, the recommendation you get from any system, even the most sophisticated one, is honestly not much different from tossing a coin. Now, it can still be acceptable for a website with that is not Netflix, or a media platform that is not Netflix. In the end, what the system is still producing is anyway a suggestion. Maybe not a suggestion that the user may like with great chances of being liked, but still a suggestion. But if you are instead not a media, an average media platform, or an average or low profile website, but if you are a giant in the industry, you want to at least try to be as accurate as possible. So in this case, you need to find a way to arrange an ad hoc algorithm that can try to make up for missing data in the best possible way. And this is, in the end, what Netflix tried to do already in 2006 with the award, a $1 million award. And they obtained to start working with a much better algorithm than the one they had in production till that moment. So this also explains, hopefully explains, why one of the things that we said earlier. So that when it comes to a recommender system, there are essentially no middle way. So either you work out a sort of relatively naive solution, or you need to go with a very sophisticated solution with no middle way, no middle ground left in the middle. And when it comes to this, so when it comes to trying to build up a sophisticated solution, you realize that it stops being a matter of training, of just training an algorithm, but it becomes a matter of building, testing, and then training a learning pipeline that is a real learning machine. Now, let's have a look at some code. So on the screen now, you see an excerpt of the sample application that we will discuss in just a few moments within Visual Studio. This shows the key steps you need to go through when it comes to training with ML.NET recommender module. The first line of code starts with an object called ML context, and that is the entry point in the ML.NET machinery. Earlier, we made a sort of comparison between ML.NET and Entity Framework, and the metaphor can be continued by saying that ML context is nearly the same as a DB context is in Entity Framework. And then on the machine learning context, we call a task. A task is a sort of silo of functionality that is fully dedicated end-to-end to implementation of all the algorithms the platform ML.NET supports for that particular task. So for the recommendation task, we take the list of trainers of the algorithms available for training, and we pick up the only one that is supported currently, which is the matrix factorization. And that is saved to the trainer variable is our algorithm. We append the algorithm to the data processing pipeline already built. And then we call the fit method, the training pipeline. We pass as an argument the data view, the test, the data we want, the data set we want to use for training the model, and we obtain back a new variable, which is called, in this example, the model. That's it. We have the model. What is a model? Concretely in ML.NET, a model is a zip file that essentially groups together multiple objects, serialized objects that form a graph of expressions to be calculated. In the end, a trained model is, in very abstract terms, is a mathematical graph that has to be calculated, that receives some input data, does some calculation, and produces an answer. In the very simplest scenario, this math graph of calculation can be assimilated to a polynomial. It's usually something much more sophisticated than a polynomial, but you can think of a polynomial as a very basic way to represent a trained model. So the model can be a way in which you serialize as a developer the information that will let dynamically to recreate a polynomial for calculating the value on some particular data points. Okay, so once we have trained that model, we have the next problem we have to face is how to have at least a rough idea of how it would perform in the real world. So we face the task of evaluating the model. ML.NET allows you to call the transform method on another data set that contains the data we want to use for testing. Again, this step is very similar conceptually to running some code through a battery of unit tests. The variable we obtain, a prediction, is then evaluated into a matrix, and the matrix, which matrix you use, the root, mean squared, error squared, there are several of them, gives a measure, usually to data scientists, not to regular developers like me, gives a measure of how good the model was, at least on the test data. And finally, if we are okay with the results, the current status of the trained model, we save it back to a disk file, which is, for ML.NET, nothing more than, again, a zip file. And that's it. So we produce, at the end of this algorithm, we have a zip file to share, deploy to production, and start using. How we would use it? We need an application to consume that model. Now, this is where, in particular, ML.NET comes particularly handy compared to Python and other machine learning environments. Because what we typically do when we work out machine learning solutions with Python is, okay, we have the model, we are okay with the model, we are satisfied with it, we have now to make it available. And the only reasonable way in which you can make a Python model consumable is just putting it wrapped into a web service, in which when it gets called by any application has the problem of latency from the caller to the web service and back. Acceptable, but with ML.NET we can do better. We can directly embed in our host application the model. And what we can do, here is what we can do with if the host application is an ASP.NET application. So here we have a sample rate controller. Again, the context is an ASP.NET Core application. This rate controller class has an internal rating service variable. And this rating service variable is an application service in the application that receives, that's interesting, something injected from, a value injected from a mysterious prediction engine pool. I will get back on this in just a few moments more in detail. So in other words, when you start the application that needs to have support for machine learning ML.NET models, in the startup of the application, you arrange a prediction engine pool that allows you to generate on a per request basis quickly and effectively with minimum consumption of resources, of server resources, an instance of the prediction engine that will consume the model to produce, given some input, predictions. And here is a method recommend we can expect to have defined on this rating service class. User movie input, that's exactly the input we receive from some user interface. So this is the user, this is the movie. Tell me how much this user is expected to like this movie. Then the method predict on the rating engine that we picked up from the pool receives the input data, returns prediction, and the prediction is in the form of a class that depends on the way in which we trained. In the end, we got a number, and this number is the response that we have to find a way to present nicely to users. Here is instead some graphical user interface. This is the way in which you can very nicely pack up a UI on top of machine learning. So I'm the user 23, the movie is 3 to 4. Of course, imagine that the user has a name, or it could even be just the logged user in the application. In more real world scenario, you have a year list of movies that in the end is matched up to an ID, whether a number, a GUID or something, and then you push the button, should I watch the movie, and then you get a response. If the response in the screenshot here is 3.43, that is reckoned, but it's a decision, business decision, greater than I think 2, then you would definitely love it. Otherwise, if it's lower than 2, then the UI shows a thumbs down and is not particularly enthusiastic about the fact that you may watch the movie. So let me switch back to Visual Studio now. Let me switch screen. Let me go on Visual Studio. Yeah. Okay. And now in Visual Studio, you see the sample project that I will make available if you are interested for download. It's a Visual Studio solution that has 3 projects. One is the model, just a simple class library that contains the data that go in and out of the model. So we have this rating data that is a class that describes the user ID, the movie ID, the rating, and not used in this example, but you can even have a 4th column that indicates the time in which the rating was given. And this is potentially a way for you in the training of the algorithm to give a different weight to ratings that are too old and give more relevance to more recent ratings. One point to notice here: everything you use for training has to be a number, regardless of what was the type that in the ideal world would describe that content. So timestamp is usually a date, but the date has to be turned into numbers to be effective in the context of machine learning. Everything has to be a number, in a float number or an integer number in machine learning. Rating prediction is the other class that represents the output from the model. So in the model we pass a rating data class with up to 4 values, ID of the movie, of the user, and the rating, and we receive a class called rating prediction that essentially shows a float representing the score, so the actual response, how much the user is expected to rate. And the score is typically a number in between the range of valid scores the system allows. So if the score goes from 1 to 5, score is a float number in between 1 to 5 interval. And then it's up to the business logic of the host application to decide when good is enough. So 2, 3, 4, you decide it. Okay, so these two classes are wrapped up in a class library, and in such a way, this class library can be shared between the web application host program and the training console application. The training console application is up here, and it's essentially a console program that just has a single call to this recommender.execute method, and all the magic takes place here. What we do here is, in first place, we load from CSV files the data set for testing and for training. Then we build up the processing pipeline, which is up here. So in first step, we just encode user ID and movie ID just to make sure that they are numbers. We take a date and turn the date into numbers, even though this feature is not used in the sample, but I still have some code for the transformation if you're interested in that. And then we configure the matrix factorization trainer algorithm, specifying what is the label column and how many number of iterations the algorithm has to go through before presumably the error is acceptable, and other values that are specific, other hyperparameters specific of the algorithm, and then the code that you also spot on the slide earlier. In the end, a zip file is saved. Now, let's move up to the, I would say, most interesting part of the story, the sample ASP.NET Core host application. Here we go. Plain ASP.NET Core. Let's take a look at what happens in Starttop, and there is this particular pieces of code that are of some interest, some high interest. First, I build up a variable that contains the path to the zip file, which is included and deployed as part of the application under this ML folder. I have the zip file produced during the training step, and then I add this call, add prediction engine pool, so the system, so the web application now endows itself with a pool of prediction engines, in particular prediction engines based on this model and accepting this input and returning this output. So in the end, the role of this pool is effectively and quickly giving you new instances of the prediction engine, which is a method that takes a rating data and returns a rating prediction, making some calculation as serialized in the zip model path. Okay, that's it. Now let's move up to where the action takes place, to controllers. We have here the rate controller class. This controller class is, as you can see here, this is invoked through the post of a form, and user movie input is simply a class that via model binding receives input from input fields put in the form. Out of this input class, I have to create a rating data to pass to the prediction engine. All the orchestration is done, takes place into this rating service application service class, which is here, just a way to take most of the code out of the controller. So in this rating service, I inject the prediction engine pool, okay, and then when recommend is called, I move from user interface data to prediction-friendly input data. I call the predict. This is exactly the string that was declared when creating the pool in Starttop. I have the rating engine. I call predict on this input, and I obtain a prediction, and then the prediction is evaluated. If it's in between 0 and 1.5, the message is you better skip this. Otherwise, if it's underneath 2.74, it's give it a try, but not much hope to have it to have fun. If it's in between 2.74 and 4, give it a try. If it's more than 4, hey, you're gonna love this movie. You have to watch it. So let's try to run this sample application and see just live what happens. Okay. Here we go. This is the user interface. So now this user interface, oops, the user interface just shows user ID, and of course, again, the user ID, but in the UI, typically you want to have the name of the user or any other easier way to identify the user. Much better way than just entering a number to identify the movie. So let's say I'm user 34 and I want to see the movie 789. Should I watch it? It takes a moment to think, and then hope something went wrong. I don't know exactly what went wrong, but the other try. Otherwise, it's a typical. Okay, yeah, maybe the movie was not in the system. Anyway, give it a try, but not much hope to have fun. And the actual value calculated return from as a response from the prediction engine is 2.13. That, according to the transformation rules in the sample controller code, turns out to be a give it a try, but not much hope to have fun. Now back again to PowerPoints for the wrap up, for the final wrap up. Let me switch back to PowerPoint. Okay, here we go. Now this is a slide that recalls a paragraph or a section that we have in all chapters of our ML.NET, Programming ML.NET book that, by the way, I think just was started being available on Amazon yesterday. There is the machine learning Davis advocate. So the point is that we try to make is no matter how many million articles you find and posts you find over the web, you may find over the web that show how easy, how trivial it could be to solve a problem. Having to do with machine learning to solve real-world problems is not easy. It's never easy. Almost never easy. But not because machine learning or ML.NET is not powerful, because the problems are really interconnected, intricate, and hard to solve. Let me tell you a brief anecdote. Not that many years ago, but ML.NET was already available, publicly available. At a conference, I had a chance to talk to some of the people from the team that at the time were on the team. And at the time I was working in the energy industry, and my focus was trying to find a way out to give a reasonable estimation on when a wind turbine could start showing age and be in need of maintenance. So predictive maintenance, if you Google for it, is a very hot topic. And the guy from the team, the person from the team, just show me, oh yes, there's a nice competition on Kaggle that I found out yesterday that shows how you can do it. But we also have gonna have something coming up in ML.NET that can help you out building a solution out of this. No way. No way, because in the real world, when you get to talk to the real energy utilities, you find out that ideally you would need to have one model per individual turbine, and the turbine, and there's the number of turbines in a plant, in a power plant, are in the order of tens or even hundreds, and a utility has hundreds of power plants all over the world. So it's very, very, very hard to arrange a made-to-measure effective solution. That's why in the industry you find for that problem half solutions that try to implement intelligent algorithms, but software algorithms, not ML, not machine learning algorithms to solve the problem. And similarly, when you approach problems from the finance industry, in sports actually we are in a way luckier, because most of the time, if you are great at working with relational data, with data in general, transforming data, you can achieve interesting results that are enough to keep the industry and the customers happy and satisfied. And our MatchMatcher challenge is one of the most sophisticated things we have done. But also, just to keep on the word on the topic of sport, match predictors that could tell you who's going to win the match, those are completely nonsense, because a match, whatever sport you take, or whether football, volley, basketball, tennis, or whatever, is subject to the human factor, and it's nearly impossible to make a prediction that makes sense. What you can ideally try to do, but that's a very sophisticated task, worth probably much more than $1 million prize award that Netflix paid in 2006, is trying to identify the time during a match in which there is a change in the momentum that could, move the bar of the victory from player A to player B, from team A to team B. Back to matrix factorization and closing up the conversation of today, even though machine factorization is the most effective algorithm for recommendation, implementing it beyond the packaging that we get out of ML.NET and other frameworks in other technological stack is not easy. So getting, that's a good news, a naive solution. If a naive solution is acceptable, that is fairly easy. If you want to look for much more accurate solutions, then you have to invent probably completely from scratch, an approach. And this is a pattern that doesn't apply just to recommendation and matrix factorization, but is, in our opinion, a general law of machine learning. Thank you very much for your time.
Awesome. Thank you so much, Dino, for speaking with us today. Really appreciate it. There's some few folks left. I just wanted to give a couple of moments to see if anybody had any questions.
Yep.
I wanted to say thank you. This is Kay. Thank you. And I have questions, but they are literally forming in my brain as we speak. So what would be the best way to transmit a question that comes to me in an hour or so?
So what was the question?
So Kay's asking, how can she ask a question potentially to you? Kay, I will say, we do have a Discord channel.
Okay.
There's a link on the Meetup site, and there's probably 100+ folks in there. It's a great place. There's a help channel in there. Great place to get in there and ask questions.
Okay.
I've taken advantage of it myself many times and gotten a lot of help. So.
Well, okay, no, sorry. For a second, I thought that the question was how can I formulate the question to have the machine some sort of machine learning answer. So I'm sorry, I was too much ahead of today's technology.
Oh no, you were way ahead of me. I'm looking at something that addresses emerging technologies for healthcare information. And I work in a space where much of the programming that's been created on the ground is real, touching the real world. But the medical observations of the average person are not as sophisticated as, research, for example. And so a question that a person might ask, for example, and you use this word sugaring, which I thought was really interesting because it was what I was thinking about at the time for a pregnant woman with diabetes, right? But who refers to that as sugar, right? And then her posing a question and getting something useful, from her post or query. You said that process for, I guess, creating the question has to be customized or custom created every time. Is that what I was hearing you say? Of converting to the prediction friendly question. Are you saying those don't exist? That has to be created like every time and it's kind of application specific?
So if I got it correct, you're talking about maybe I'm not sure I got the sense, but probably you're talking about how we can create some sort of frequently asked questions on a topic or no?
Yeah, I'm asking, are you saying, because you said something there at the end that essentially you're creating something custom every time, right? And I'm asking, is it because of that thing of having to convert from the query to the prediction friendly question? Because for me, like the sector that I work in, it's healthcare. And
okay,
so
let me summarize briefly the experience that probably I think it could be an answer to exactly your points. So one of the projects we worked was just in healthcare for one of the largest hospitals in Europe, and it was a way to help the patient in a particular area of care in the hospital to have quickly and easily answers to common questions. But it was not simply an FAQ website, because they already had it. It had to be an interactive kind of way. And in the end, if the patient was not able to close the ticket, she was opening, just WhatsApping the question, then the patient had to be redirected to a real person taking care of the question and the issue. But so in the end, we used a chatbot, we used some hard-coded pieces of machine learning, so Azure services for interpreting questions and for natural language processing. But in the end, to solve the problem, we had to build out a workflow that could drive the patient from the initial question out to an answer that could close the ticket she opened by asking the first question. And this is not something, or most of the time, this is not something that a smart, extremely smart and functional piece of code like the natural language processing tool or the chatbot here there could solve. You have to build out a workflow that, composing together these smart pieces of artificial intelligence ready-made, could build up your own solution to your own problem. I'm not sure if this answers completely the question, but I guess that this is the best.
It does. It does. Thank you.
Okay.
All right, cool. Well, again, thank you, Dino, so much. I am going to stop recording here. We'll get this uploaded to YouTube hopefully later today. Again, thank you so much for being here.
Thank you for the opportunity to talk and share this information, and maybe in the future we can make it again up and running.
Perfect. Thank you so much. This is great. Thank you again.
Bye-bye.
Yeah, that was great. Thank you.